Hey everyone, welcome to Lesson 1B of Scientist AI. In the first one, we dealt with the simpler linear systems just to kind of give us that foundation of how learning works in general. A lot of that math, a lot of that those high level concepts still absolutely apply to the deep learning setting. But now we're going to get into deep learning itself. We're going to see what is different, what changes, what happens to some of the same math that we had in the first lesson, how things get changed, warped, converted, so that we end up with a much more powerful, flexible model. And of course, that's why it's underlying today's technology in AI. So let's look at how learning happens from a deep learning perspective. First, I'm going to start with kind of a surface belief that a lot of people probably have if you're not exposed to this much already. And that's kind of thinking that maybe learning only happens one way, kind of the traditional statistics approach. So what is learning? Well, most people intuitively believe that learning works kind of like this. You collect data. The data already has features, right? And we looked in the first lesson, literally the columns, right, of the table. And then the model learns essentially how important each feature is. In other words, the structure is already there. If we had some kind of relationship, we usually think of this as learning some kind of function, and we're going to go from the X set to the Y set. That's how you want to think about it. These are the inputs. These are the outputs, right? And that's what learning is, right? You want to learn what this function is. You want to learn the mapping between the two. So the structure, the assumption often is that the structure here is kind of already there. Structure being the relations that govern which points map to which outputs. Remember when we set up the linear model, it was essentially saying, here's the playground that you have to work in, right? You can still kind of figure out exactly how the mapping or how the outputs are going to get produced, but the rules that kind of govern the input to the output are already pretty set. So learning just kind of assigns weights, right? Here's your playground. Just tell me how important the features are, right? Up here, the columns that you're doing, the attributes of whatever phenomena you're looking at. Just tell me how important these individual ones are relative to each other, but you still have to play within this kind of playground, right? So to be clear, structure is not the data points themselves, but kind of the regularities in the mapping, okay? So I think that makes sense. Remember from the previous lesson, we had this kind of mathematical framing, right? We said that if we're looking at the data here, right, we can say that let's say one row of that data set, which we said X superscript I, is belonging to the real numbers by dimensionality D. So dimensionality D was literally just how many features you have in the table of data that you're using to train your model, right? Literally the number of columns. So we could call that a fixed feature space, right? Because if you remember what a feature space is, it's kind of like taking these columns and then literally building basically, if this is A, B, and C column, we'll go A, B, and C, literally like a graph, literally like a chart, and then your data points exist inside that space somewhere composed of, in this case, the three features. If we just grab the three columns, if we grabbed all of these, this of course would be a high dimensional version of what you see here, but this is the feature space. The data lives inside that, right, as data points, right, where their location inside that feature space is literally dictated by what their values are, okay? So what we could say then is, or what we did say in the first lesson, is kind of the function that we were trying to learn, if you want to think of it like that, was basically we had a weight vector, right, which got transposed. It has a dot product with the input data, and then it has a bias to it. And of course, this is essentially just equation of a line, right? Similar to basically mx plus b, but of course, this is going to be a vector of weights as opposed to just one value. But same idea. So the feature space here is kind of assumed. It's not questioned, right? We build the feature space out of whatever data we have available. And that's it. It's essentially fixed. That's the simple linear system. And that's typically what people kind of think of. You're going to do a bunch of statistics or just maybe kind of traditional machine learning, you might call it. I'm just going to collect data, these columns, build the feature space. That's the playground that I play in. Now, we see this kind of belief everywhere, right? What I might call kind of the traditional belief of learning. So I mentioned kind of statistics, right? You choose the right variables, then you fit the model, right? You often see this with 2D plots, right? You see this in papers everywhere, where basically you're going to go collect a bunch of data, okay? It's in a table. It's kind of like an Excel spreadsheet, right? Boom, whatever. You know, but maybe you're just like grabbing two of these and you see these two-dimensional plots and there's data scattered everywhere and they're going to fit a line on it. Okay, so you choose the right variables and then you fit the model. The better you do this, the better it fits. Maybe it's not linear. Maybe you kind of get a little bit of flexibility in there, but you're trying to fit the model to the data points, right? Think about education, just more conceptually, right? Learn the steps and then just apply them harder. Kind of the same idea, right? Again, there's this kind of static almost mapping between the inputs and outputs. That's the playground you get to play in. So it's kind of like, here's how education works. Here's the curriculum I'm going to give you. Here's the exams that you have. If you want to do better, just apply the rules that we tell you to do and just apply them harder. That type of education, that type of learning. Right? That's how people think of it. Again, on the surface, it's not wrong. The more kind of gamified environments, that's exactly how it happens. Gamified being everything is kind of very explicitly defined. It's kind of simplified, standardized testing, right? Kind of has to work like that. Another example would be economics. We know the variables, we just need better estimates, let's say. So you see this kind of same underlying assumption about what learning is everywhere, right? And you could kind of re-express that as the coordinates are already correct. So collect whatever data you want, try to fit the model, but the coordinates, right? Or let's say the axes and kind of where the data sits, more to the point, is what it is, right? Like those aren't going to change. What else is there to do? That's kind of the surface level belief. Okay, now let's think about where that basic intuition actually fails. Let's apply the same logic to what you might call the complex domain, i.e. real world, right? The real world where you got lots of different variables and these kind of simplistic notions of playing in a very kind of almost static mapping between input and output just doesn't really apply. So let's say people apply this logic to complex domains, I'll just call that, and they notice some strange failures going on. Like models work well in simple settings, but then all of a sudden collapse in the real one. A nice example might be, I think I mentioned this before, you got linear regression, it seems to work really well, but let's apply that to something like, I don't know, facial recognition. I mean, you could try. You could collect all the features of the face, right? The nose, the distance between the eyes, the lips, and whatever, all the attributes you want. You can go a million if you want. Do a high-dimensional version, right? Kind of a multiple linear regression on that and try to fit the model the best you can to try to predict whatever it is about the image, whatever it is about the face, the person's identity. You can do it. It's not going to work, right? The model's going to collapse in those real-world settings. You can't do speech recognition with simple linear systems. You can't do all that kind of stuff. Really, really bad if you try. Adding more data helps less than expected, actually, in this situation, right? You can say, well, no, I can still use a simple system, okay? Because here's my playground. It's still input mapping to an output. I just need to collect a lot more data, right? A lot more data. And some people, as we start getting into deep learning, you might think that that's kind of all deep learning is, right? It's just the same type of traditional statistics or traditional machine learning has always been here, and we're just throwing way more data at it, right? No. This is not going to work. No matter how much data you collect, this basic setup is never going to do facial recognition, never do speech recognition, never do whatever kind of a categorically hard problem is that you want to define. So adding more data actually helps less than expected. This is another one kind of where the intuition fails about this simplistic version of learning. And then also explanations themselves actually kind of become fragile or inconsistent, right? So again, kind of using kind of linear techniques, you might say, well, I'm going to find out how important each of these features are, and then I can use that to kind of explain things, which is kind of a traditional thing to do. Statistics, machine learning, right? We found out that this part of the stock market and this part seems to be driving the stock price the most, so we're going to explain. The problem is these explanations start to become quite fragile, they're inconsistent, they don't really work. It's almost like this simple setup isn't really a good way to put the playground box around reality. And that shouldn't really be surprising. But this is a lot of what most people learn when it comes to statistics and even kind of simpler approaches to machine learning, right? Okay. So let's think about kind of like a mathematical signal of this failure that I'm talking about. Okay. If the true structure is not what you might call linearly separable in the given coordinates, then no choice of that W is going to help. Remember when we were talking about, let's say we wrote it as Y hat, and we've got a W and the transpose and the input data plus the bias, basically our linear model, and you can keep trying to learn, and there is learning here, right? Remember we have, you can have the step size, you can do gradients on this, you can try to keep getting better and better weights. But if the true structure of reality or whatever phenomenon we're looking at is not linearly separable, which is what this requires in the given coordinates, right, then no choice of W is going to help. So one way we could actually express that, because I like to express things kind of definitionally with the mathematics, so you can always go back to it and say, well, what do you mean linear models can't work? What do you mean, well, here's a way to kind of lay that down. Okay, might be some funny symbols here, but just bear with me and I'll explain them all as I do. This one's an R. So we're going to go this kind of backwards E, let's say structure, S, and we'll have this kind of funny symbol. You guys, a lot of you probably know these symbols already, but I like to talk like that just in case you don't, because you don't need to be intimidated. Okay, and then we'll go to D. Okay, so what am I saying here? Okay, so we can think of this as kind of like a mathematical signal of failure that's happening. So this is there exists, okay? Right, there exists, we'll say some property or regularity the task depends on. I think that's kind of, obviously that's what structure means. Okay, this is not a subset of, okay? The span, we can say, is all linear combinations of those features. And these guys here, we can just say the input feature vectors. So the coordinate axes of the original feature space. So again, if you didn't see the first lesson, go back to it, right? But these x's are getting pulled out of literally the table that we're looking at, right? You want to look at one of the rows or all the data, okay? So what does this mean? So this is kind of like a mathematical way of saying, but it's also a truth, right? That there exists some relevant structure that cannot be expressed as any linear combination of the given features. Okay, when I keep putting dots above the columns, I'm like the features of the data set, right? The columns of the data set. Hopefully that makes sense. Okay, so that's all this is saying, right? There exists some relevant structure that cannot be expressed by any linear combination of the given features. Kind of the mathematical way of saying that. So no matter how you weight the existing columns, you cannot express what actually matters. I'm just really driving this home because you run into this a lot where, people kind of chalk, let's say, deep learning up to just, it's just statistics with a lot of data, or, it's basically, you've got little almost linear regressions or linear models in there, and then you're just stacking the linear models. So isn't it still kind of a linear model? We're going to see how this is just absolutely not the case, right? Just because you start with simple, basic things, the way you bring them together under complexity really changes everything, right? And that's a good kind of almost definition of complexity, right? You have a lot of simple pieces, you have a ton of them, but through their interaction, you get this kind of emergent behavior that does something extremely different, very different. It does not trace back to the small pieces that went into it. Okay, so this is not about insufficient data. It's about insufficient coordinates, actually. Insufficient coordinates, okay? So again, we think of things as a feature space, right? They play out in some feature space. We have axes, and the coordinates tell you where they are on those axes. But no matter what you do in that space, if you're thinking in linear, simple terms, it just really isn't a good approximation even of reality, let alone the ability to engineer a system that does good predictions with it, on it, right? So where this simple intuition fails, we've got this mathematical signal of failure. Let's think of some cross-domain analogs, and we're going to get into a lot of the good math and science in a bit, but just, again, I want to use the real-world examples to help people understand, right? So think of climate modeling, right? You can say known variables fail to capture emergent patterns, let's say. Like climate modeling is hardly a solved problem space, right? So you can collect all the data you want. If you're going to go put it in a simple linear system, it doesn't matter if you know some variables that fail to capture. Remember, I was talking about the emergence, right, of what complexity is. And you better believe the climate is going to be a complex system that has emergent properties to it, right? Whatever that is. You've got Earth, you've got the climate, you've got wind patterns and cloud formations, and basically ad infinitum, all these things going on to actually predict what the weather is going to be in one location. It's not a simple thing. Medicine, right? Biomarkers don't really generalize across populations. Just skill learning in general, repetition without insight, kind of plateaus. You kind of think of learning simple linear systems almost more like repetition. It's barely any learning there at all. It's got some idea, right? Like we said in the first, I said in the first lesson, right? Like if you're fitting a model, it's kind of like learning. But if you don't have a flexible playground to do that in, if you're just like doing a straight line, you can barely call that learning. It's almost more like repetition. And, you know, the insight in the real world is just going to plateau. You're not going to, again, understand what features even mean or how they're supposed to be mixed together, right? So the same thing ends up breaking every time. Linear thinking applied to non-linear structure. The real world is not linear. Like ever. Like ever. Okay? Sometimes you can get away with a linear approximation to things as a real simple, almost more platonic, if you will, way of thinking about things. But it's almost more of a pedagogical trick than genuine science, I would argue. Even though, you know, of course, the rebuttal to that might be, but you see linear methods everywhere. So many psychologists use them. So many, yeah, I know. And that's not necessarily a good thing. It's an extremely convenient, easy thing to use. Sometimes it might be a bit appropriate. But no matter what you do, no matter how many tricks you play in the playground, it still comes back to kind of what this expression says here. There exists some relevant structure that cannot be expressed as any linear combination of the given feature. I wouldn't even say some relevant structure. I would say the relevant structure in reality can just not be expressed as a linear combination of given features. No matter how you weight the existing columns, you cannot express what actually matters. You can do it. You can do it pedagogically. You can pretend like this is how the world works, but you're going to keep running into this guy right here. Okay. Okay. So what is the kind of unspoken assumption here? Well, let's just clear some space off here. The unspoken assumption, and it is often unspoken because, again, you see these linear techniques everywhere. Again, there might be a time and place for them, but nowhere near as much as they kind of get promoted, I would argue. The unspoken assumption is that the meaningful structure of the problem is already aligned with the input features, just like we were saying, right? So again, we know input features belong to the reals by dimension, and then you just got to leave it at that. So the mistake is treating this, which we saw in the first lesson. Sorry, my X's have a lot of style to them. The mistake is treating this as the representation rather than a representation, right? Like, yes, you capture it. No matter what you do, if you're just collecting the data and then model that directly, this is all you're doing, right? All you have is this, and you're playing in a linear playground. Y equals mx plus b, right? And that's it. And it's just extremely restricted. There's not a lot you can do with that. This is a representation of reality, but that's not the representation, right? It's not the best representation necessarily. In fact, you should almost assume it never is. This assumption is almost never stated, but literally everything depends on it. Any type of technology you're going to build that's supposed to be modeling, predictive, reasonably approximating science, learning in general, even if you're talking about the human brain, right? At an abstract level, right? Rest assured, your human brain isn't fitting linear models, right? We're talking, it's the most complex phenomenon we know of in the universe, we know of, right? So anyway, everything really depends on this. So the hidden assumption, problem structure, input features, let's get a little bit more kind of scientific here. It's equivalent to assuming the basis vectors, which you can kind of just for now think of as the axes, right? It's equivalent to assuming that those basis vectors are meaningful or that the geometry is just correct. Like, it could be, but it's assuming that it is. There's no extra work being done because all the work comes after this, right? You just assume this and then you go do your modeling. Again, it's the playground, it's the box you're playing in. Linear models require this assumption, and here's the point. Deep learning rejects it. Deep learning wholeheartedly rejects this. So when people start saying, well, isn't it just kind of like regression and stacking? No, it's absolutely not. Isn't it just kind of, machine learning or statistics? You always hear the statistics. Isn't it just like basically statistics AI, but just with a lot more data? No, it's really, really not. And hopefully by the end of this lesson, you'll conceptually and mathematically understand why that is. Okay? And by the way, you can go look at the history, can go look at Leo Brayman's really good paper on this. Machine learning in general really came out of trying to get away from statistics. They're two very different camps. And that doesn't mean statistics is always bad. It's not. And that doesn't mean statistics can't play a role with really important validations in AI. It can. But you have to understand these are two different camps. Deep learning rejects a lot of what traditional statistics relies on, okay, primarily. Okay, a few more cross-domain examples in physics, right? You could say using microscopic variables where effective variables are actually needed would be an example of kind of getting the wrong world applied or the wrong model applied. So microscopic variables, kind of be like super simple example, you're thinking about something like temperature, and that would be more like an effective variable, something that essentially emerges out of a bunch of microscopic, let's say, kinetic activity of the molecules or the atoms that are in the gas, let's say, right? You're not going to really explain a lot by just focusing on the details. You have to raise above the system at a higher level and explain it with effective variables, right? Economics, modeling agents instead of flows, reading. Okay, let's use a real world example like reading, focusing on words instead of semantic structure, right? Talk about this a lot, being an effective reader, right? A lot of people do things word by word and they vocalize it. It'll get the job done, but it's really not effective reading if you know how the mind works, if you know how memory works. Anyway, not going to get into all that now, but it's focusing on semantic structure, kind of more global things as opposed to nitty-gritty details, right? So you see this everywhere. I mean, it gets into reductionism, it gets into all kinds of stuff. We don't need to get into all that now. But I want you to just understand that deep learning rejects a lot of what statistics has put forward. Again, it doesn't mean there's no overlap, but you have to understand that point. And hopefully already you understand why that is, at least conceptually. But let's get into some details now. Let's think about the governing structure of deep learning, okay? Now, this is really, you can say, well, what really is deep learning? What is different about it? You could say it's about feature learning or learned representation. So, again, you start in the same spot, just like statistics, right? You go collect the data, you got rows, right, or you might call examples, and you got your columns, which we call features, but that's it, right? And then you just model from there. The whole point of deep learning is to basically learn new columns. That is a real conceptual way to say it. It basically looks at this and says, these are what you capture directly in the data, but I don't think those are the right axes and coordinates of the playground we should be playing in. These probably mix together in all kinds of nonlinear ways. That's really what deep learning is about. And it's going to learn different columns, which you never see, different features, which you kind of never see, hence the black box of AI. We'll get into that a bit. Okay, but deep learning is all about replacing a single feature space with a sequence of learned representations. Okay, so I'm starting to allude to this notion. We're going to take a look at the neural network. And it's, if you haven't seen, you've probably all seen diagrams of it, right? You've got artificial neurons in there, and then they're stacked, and then they go in layers. Okay, that layering is the learning that happens with new representations. It's like new and new feature spaces. I'll draw that out in a bit. But let's get a little bit of math here to ground this. Okay, so I'm going to say, let's take a look at remember last time we looked at one row of data, right? And I'm going to say, and I'll explain everything in a bit. Okay, let's grab one of those rows and something like that. One row is one example. It's got all the features, right? So it's like one data point. Okay, and I'm going to introduce a phi here. And I won't define it yet. And we'll just say this is the first one. And then I'm not going to do any of the usual kind of linear stuff. I just want to say that it belongs to the reals for D1. Okay, oops. So what does that mean right there? So this is indexed by layer. Okay, so I could do another layer for the same row. Okay, so we'll still do xi like this. And then it's going to have another one of these phi's. Again, define it in a bit. Going to have the same thing here, but it's just indexed by the layer. And it's the exact same thing, not changing the rows in the data set. And then again, and then I'll say it belongs to the reals, and this time I'll say D2. Okay, so and we can keep going, right? And go all the way down. I'll just do one more just to say the final layer, and then we'll explain everything. Again, still the same thing that we're grabbing, right? The one row, kind of think of it as row by row. 5 for the final layer. Okay, you still got the same data, and then what we can do is actually go L minus 1. I'll explain why that's like that. Belongs to the reals, and then this will be whatever dimensionality of the final layers. Okay, so this is like looking at what your data is doing as it kind of flows through the network, okay? Because I'm indexing all of this by the layer number, okay? So let's just focus on the first one in case it looks a little crazy. So layer 1, what is my data doing that I grabbed? What is the one row of data that I grabbed out of the table doing in the first layer? Okay, so we grab it and we say, okay, here's the original data. The phi is some transformation. The transformation, then don't worry about what that is right now. We're going to get into that. It's things like applying nonlinearities. It's adding the bias to it. It's getting the dot product in there. This is all before that. Again, that's from lesson 1, other than the nonlinearity, right? So we'll get into what these transformations look like, but for now, just think of it as a transformation. So the transformation is happening on that data that we took, and it's going to have the dimensionality of whatever the first layer is. And we're going to see that the architecture of the neural network actually dictates the dimensionality. So that's already different. Because in lesson 1, we said, this is D right here. So however many columns you have, that's the dimensionality of the data set. That's the dimensionality of everything. Like that's the dimensionality of the feature space you play in. That's it, right? Here we're saying, well, no, we're going to index that. We're going to say the first one has this dimensionality. Let's keep trickling the data through the network. We get more transformations. Okay, this is what the data looks like at, let's say, this next layer. And that layer now, because again, the subscript here is the layer number, right? That has its own dimensionality, right? Why did dimensionality change? We're going to see explicitly why, but the take-home message here is that it's almost like, you know, are you squishing the data set? Are you expanding the data set? The columns are changing. The columns are changing all the way down to the final layer here, big L, whatever final transformation you do. Again, we're still looking at the same data. It's trickling through the network. L minus 1, because we could say it's not the very output. We'll take a look at the diagram later. So it's 1. It's just before you get to the output, this is the final transformation that happens. And its dimensionality belongs to whatever that final layer dimensionality is. Okay, again, we're going to see what this means explicitly, like how the dimensionality changes. But the take-home message here, right, if someone was like, you know, what's happening to the data in deep learning, it's this, right? Right? Here's the data, then here's the data, and trickles all the way down to the final layer. Look at how its dimensionality is changing for some reason. And that's really the take-home message here, is the dimensionality changing. So another way we could write this here, just a little more simply, is you're like, you know, what is happening to any given data point in your data set when it comes to deep learning. We could say, well, you start with the initial. Okay, that's O, okay. And then it goes to, it undergoes some kind of change to its next. It's still the same data point, but it's got some kind of change, right? Got another kind of change. You could say this is the layer index again, right? All the way to some final, you know, I don't know, right? Dot, right? X, I, big L, okay? And so you're saying the data here just keeps changing through the layers. It's basically the same thing we just showed with the other formula, but just a bit simpler, right? That's the take-home message here. Okay, so I think you get that. Now we're going to kind of take a little more conceptual look at what that means. Like, why does the dimensionality of the data change? Because again, the linear assumption, the simple assumption is you just take the data, those are the columns, and that's what you get, right? So nothing about the data point changes. It's actually only its coordinates that do. So here's our initial one. Now let's say we start going through the deep learning. What happens? Well, now you kind of think of, okay, here's the data going through again. Okay, but this is unfixed. Okay. Whatever columns you had, I don't know what columns you're going to get when you're done. You're going to keep going, right? And this is just conceptual, right? I mean, it's not like the columns in the original data set are actually changing. I mean, the data gets re-represented within the systems of AI, but conceptually, this is the idea. You keep getting new kind of representations of the data, and you could say, you know, let's just say this is A, B, C column, okay? So we'll just go A prime, B prime, C prime, A prime prime, B prime prime, C prime prime, right? These are all going through changes. Something is happening to the data columns themselves. They take on a completely different meaning, or very different meaning. So a very conceptual, high-level way to think about what deep learning is doing with the original data as it goes through, trickles through the layers. And again, we'll take a look at what these layers look like, is new columns, right, created. Okay, now that's just a pedagogical kind of thing. I mean, again, it's not like the columns of the data are actually changing, but it's a good way to think about it because it's a good way to think of the feature space as being originally created from the columns, and the feature space is what is now being learned. It's what is being changed. It's a learned feature space. So we still get to the point where we have one of these, but we can't just call this ABC, right? You know, it's maybe A prime prime prime, B prime prime prime, C prime prime prime. Things are the axes are changing, and the coordinates, wherever the data points live, are changing. I think a better way to say that is the data now lives in kind of a different space, right? Again, deep learning is rejecting the idea that the original space you grabbed as the data table is the space you're supposed to be playing in. It rejects that, right? Because that's kind of like assuming, especially for AI, like that would be assuming that the human brain brings in data directly like that and then has, you know, kind of a playground that is specifically defined by the original kind of attributes you viewed, I guess, and then everything's linearly separable and yada yada. It's a way too restricted playground. Deep learning says we're not going to assume that at all. We're going to warp these. We're going to massage them. We're going to change the coordinates themselves so that the data points, even though in some sense they don't really change, the playground that they play in does. That's feature learning. You're learning what those features are supposed to be. Okay? So that's conceptually what's happening with deep learning. That's why it's very different. That's why it's really not just statistics. Okay? I think you guys get that now. Again, we're going to look more about how this kind of stuff happens, but it's important to have the right mindset going in. Right? Okay, so most of you have probably seen drawings of neural networks. So let's kind of do a simple one. Like, what is it, right? And so, you know, it's more or less loosely modeled after what we kind of think the human brain is doing, right? At least that's definitely kind of the original inspiration, and some of that is still held true, and then there's been deviations from that. But the basic idea is, you know, we think the human brain has neurons, so we're going to make a computer program that has neurons, artificial neurons, and you're going to basically kind of wire them all up so each one kind of talks to the other one. So this guy, let's say, is connected to all four. This guy's connected to all four. Same thing, right? And everything gets wired up, like this. Boom, 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 boom. Okay, now it doesn't actually have to be like that. Like, you can make sparse connections, you can do pruning, there's all kinds of interesting stuff you can do here, but just basically this is the idea. Okay, you're gonna wire them all up. So that's the neural network. And we say, just for kind of nomenclature, right, this is the input layer, okay? And we call these guys in the middle hidden layers, okay? And, hidden, there's a number of reasons you can say why it's called hidden, but basically they're doing things that we don't really know, okay? This is kind of the black box here, right? And then this is just the output layer. So the things that you can look at directly in a neural network, deep learning, this includes technologies like ChatGPT and everything, right? Kind of just more sophisticated versions, but essentially the same thing. Yeah, we know what the input layer is because that's just the raw data. So if we literally have, let's say, like 2 data points coming in, it would be like that. Is one way to think about it. And then you get, this could be like a classification, like maybe it's going to, classify between cats and dogs or something. So maybe that's cats and maybe that's dogs. Some kind of binary classification. There's different ways you could do this. It doesn't really matter for now. You know what that is. You know what this is. You don't really know what this is because of the way the learning happens. It's so complex. The features are getting learned in here. Everything that we talked about so far, that's where the features are getting learned. And they're getting kind of amalgamated and warped and consolidated in ways that you just can't reverse engineer. Okay? Think of these guys in the middle here as essentially new coordinate axes, or new coordinates end axes is probably a better way to say that, right? Because axes are essentially directions that you play on, and coordinates are the value you have on those axes. Okay, but for the sake of simplicity, just think of it as, like, again, you're just learning new things. Now, more specifically, what I mean is an individual neuron can be thought of essentially as one of the axes. You might call them coordinates, but one of the axes. That's one. So if we take these three, okay, these are these three. Those are your new ABCs, let's say, right? Okay, that's a different feature space than whenever you came in with whatever kind of assumptions you were making up front. Okay, and then these guys are going to be another three. So these guys, as it goes through, it goes from left to right through the network, the data trickles through. Okay, so this is the first feature space. This guy learns the next feature space. So kind of like A prime, B prime, C prime, or prime, I guess I only had the one. Okay, and then you can keep going. So obviously these networks can get huge. Okay, they can have a lot of depth to them, a lot of layers. They can have a lot of width to them. You can stack a lot of neurons. These don't have to be the same. Again, there's all kinds of things we can change. We're not going to get into that right now. The take-home message for this lesson is I just want you to think of these as the new kind of vectors that are used in the new feature space, the new coordinates, the new axes that are being learned. Okay, you're recasting the data into new coordinates. Okay, that didn't exist before. Now we're going to take a look at what those neurons are actually doing mathematically, but just again conceptually, that's essentially what's happening, right? Okay, so what is each layer doing in that network? Well, like I said, each layer mixes all the previous dimensions. So you came in with whatever dimensions you had in the data, straight out of the box feature space. You get some interesting mixing. Now, the mixing shouldn't be surprising just based on the way I've drawn this, because all the neurons are talking to all the neurons, right? So there's this mixing that happens. It defines literally new coordinate axes for the new feature space. You can think of this as redistributing information geometrically. Okay? And the word geometrically is kind of being used in this abstract way. Things that we'll get into later when we talk about things like manifolds and stuff like that. But if you have a feature space, the playground in here has some kind of geometry to it. It's kind of almost like the topography of the land dictating what you can and can't do in a way, where you can't go, where the possibility kind of nooks and crannies are, I guess, within the spaces of possibilities. It's not that unlike saying you've got some function and you're locking in rules from X to Y. It's just way more complex than a simple mapping. There's a kind of a geometry to it, right? Almost like a topology, a warped space in here that dictates how you play. The idea, and you see this in a lot of science and problem solving computationally in general, is if you can get the right geometry, then you can compute things more effectively, because the geometry, if it's going well, is reflecting the geometry of nature itself, the geometry of information, right? So if you collect a bunch of information, right, the original assumption is this really basic thing, but what's the actual geometry within that feature space? What does the playground look like? That might sound kind of hand-wavy, and it's obviously extremely conceptual. We'll get more into that later, what exactly that means. We'll define these things mathematically. But this mixing, right, this new feature learning, this blending, this amalgamating, this smushing together of columns in the data into new columns, quote unquote, new coordinate axes, that's why AI is a black box. That's why you cannot reverse engineer. No expert in the world is going to pull back the layers and know exactly, what features were important, for example. Because even the word features almost loses sense of meaning the way we normally use it. So think about a real world example would be like an AI ethics, right? Someone in ethics might say, well, these AI boxes, these black boxes, we got to make them explainable. Well, what does explainability mean? Explainability essentially literally means, there's different versions of it, but essentially the leading way you get a model to be explainable is you go back to the columns of your data set and you tell me which ones are important. Right. So, for example, if I was doing a model that was predicting whether or not you should be accepted to get a credit card, and then you get denied, and then you come back and say, okay, I want to know why I was denied. Well, that's literally going back to the data set and the model telling me which of these attributes that I collected about you stood out, leading to the prediction that it gave you, which is to get rejected. So when you think about explainability, think about literally highlighting certain columns in a data set and pointing to them and say, here's what the model thought was most important. Okay. Now, something like a linear regression, simple linear models, you can do that because the original representation of the data is not changing. But that's not the case with deep learning. Deep learning is mixing and matching these together in ways that nobody can understand. Because the word understand, the way people use that is they mean causally. right? Like I want to see what bumps into what. I want to see what was actually used and how it was used. If you ask me to explain why I'm teaching this course, you want, well, first I thought this, and then I thought this, and then I put this together, and here's what I think it's going to, you want to see what bumps into what, right? Deep learning cannot tell you what bumps into what. Okay, I don't care who argues that. If you've discovered a way to get this to tell you what bumps into what and what features are important, well, you're no longer doing deep learning. That's not what it is. The whole point is to learn feature spaces and to put these and to recast the data into brand new geometries that don't have that type of explainability to them. If you want explainability, you're going to have to go back to simpler models that don't allow you to predict faces, don't allow you to do things in medicine, don't allow you to solve categorically hard problems. It's not up for debate. Now, that doesn't mean there are maybe other ways to try to get at explainability, but quite frankly, if I could put a bit of an opinion into this lesson, I think it tends to get a bit goofy the way it currently is now. I might, find hotspot neurons, like, well, this neuron was really activated during the decision-making process, okay? What is that neuron? Look at all the lines connected to it. What is that? Do you know, maybe if it's the first layer, maybe I kind of know which features were being blended. What if it's all the way over here? Right? I mean, it's the output that's giving the prediction, right? And quite frankly, this is how the human brain likely is at a high level. I'm not saying the process is exactly like deep learning, but obviously just because somebody gives you an explanation doesn't mean that's actually how the input's causally connected to the outputs. I can give you an explanation, doesn't mean it's real. It doesn't mean I'm lying, it's just humans need narratives. Humans need to think in simple linear terms, so that's how we tell our stories. Anyway, deep learning, right, is different. This is why it's a black box. Think of these as the axes, literally, of the feature spaces that you're learning. They have very little in common by the end of the day, by the time you get to the output, of what those original axes look like. And you have to do that because you got to learn the geometry. Okay, so now let's do, so hopefully that conceptually made sense. I want to drive home some more of the concepts. Before we start looking a little bit more at the math, we'll take a look at, what the weight vectors are doing, kind of, the dot product and all that is still there. But let's think about projection. I think this is really good. As we say, what is each of those layers doing? Okay, well, again, let's draw out the feature space. Again, I draw this in 3 dimensions because that's the only thing we can visualize, or the maximum thing, right? 0, 1, 2, and 3, I guess. But this could be a billion dimensions, right? It's high dimensional, but the concept holds. So we're going to have a data point in there. It's playing in that space, and we'll do it as a vector because it is a vector. That's how we represent the data within these systems, right? We saw that in lesson 1. And then I'm going to draw 3 dashed arrows. And again, if you want ABC here, although, sure, maybe that's the original representation from the data. Okay, then I'm going to draw 3 more vectors here, like this. Okay, and those are going to be what we'll say multiple weight vector projections. Okay, multiple weight vector projections. By the way, people who take this course have access to slides, and so if my stuff is a bit messy, you'll get clean versions of my drawings and stuff like that. This is actually what one neural network layer is doing. Okay, so each dash layer is corresponding to a different weight vector, a different projection direction, a different neuron. Okay, so again, we're looking at that neural network, right? Just really quickly, whatever it was, blah, 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 everything's connected, right? And you're like, well, what are these neurons doing? These guys are reprojecting the data to different parts. Okay, the weight vector is telling you essentially new direction, right? So if you learn, when you're learning new feature spaces, you're learning new axes, you said, right? Think of it as learning different weight vector projections. So once we go back to the math, just like we did in lesson 1, where we dealt with weight vectors, well, think of it as deep learning is learning different weight vectors now, right? Because if you just stick with the one weight vector, you can still kind of update it, but maybe it's still playing in the same space. But if you reproject it into kind of a different geometry, into a different space, right, then you get different ones. So with these if this is 4, then you might say you got like 40 projections, let's see, right? A different neuron doing a different weight vector projection. Okay, so now we're getting into kind of what deep learning is literally trying to do, right? It's like, here's your original data. here's the original vector. We want to reproject that kind of somehow differently. We don't want this vector pointing the exact same direction with whatever direction it has in the original data set. We want to project it differently. Okay? Project it differently. I'm going to keep it still kind of conceptual there. So, we'll always, throughout the course, we'll get more into, what do you mean projection? Like, what exactly? I don't want to do too much right now, but just think of it as, I want this arrow to point slightly different, right? Because I don't think the thing we grabbed right from the beginning is exactly correct. Learn different geometries, learn different spaces, learn different coordinates, project the data, make it move along a different direction. Okay? What direction? That's why we learn. I don't know, right? The deep learning is going to go through millions of iterations to figure out. Okay? But think of it quite literally as different neurons giving you different projections of the data, different axes of the feature space, right? I think that's a good way to visualize it. Okay, let's get into some math now. And because I know a lot of that was kind of conceptual and, well, it was all conceptual. So let's take a look at kind of what's happening mathematically. What is each neuron doing from a mathematics perspective? Okay, so I'm going to say, let's take a neuron J in layer L. Okay, so bear with me. We're going to say, okay, here's our layer. And for this, we're going to take a look at one neuron J. And we're going to have this sigma here, which I'll define in a second. And we're going to have kind of what we usually, this will look familiar, right? We're going to have transpose weight vector. I'm going to sub it with L, sub it with J. Okay. And then we're going to say with the data, and that's going to be L minus 1. And then we're going to have a bias there. So we see some of the linear stuff still in there, right? And that's going to be for the layer, and that's going to be for the neuron. Okay, so we're going to have this expression here. Now, you can say each neuron quite literally computes this. Okay, literally computes this. Okay, so now what do we have here? Well, we have this XL minus 1 here. Okay, I just want to pick apart the pieces. Okay, so you know what each thing is. You could say this is the current representation of the data point. Okay, so I'm just going to call that current data because, again, why am I saying things like current data? Well, we know from before that the data is trickling through this network and it keeps getting re-represented, right? It goes through some kind of change, right? It's getting warped, it's getting, right, massaged, whatever. So current data, whatever layer you're at, like if I was at the 17th layer, it would be the 16th layer's output that I'm getting. That's why you see the L minus 1, right? So whatever came before me, that's the current data I have. Then you've got this WLJ. Okay, we already know the W from first lesson and earlier parts of this one, that's the weight vector. So we're going to say that this, actually, let me just go. Okay, again, that's L. J is the neuron, L is the layer. Okay, we already know this belongs to the real numbers, and it's got some dimensionality, L minus 1. Okay, why? Well, again, every time you see the L minus 1, it's just like whatever data I received, right, at this layer. So it's going to have the dimensionality of the previous layer. So if I was the 17th layer in, the 16th layer, which could have any number of neurons to it, if it had 10 neurons, this would be 10 dimensionality. Right, and the weight vector is going to have that dimensionality because we know, even like in the linear systems, right, when we took one data point out of the table, right, you have the X being the data. Let's say it has dimensionality D because it's got that many columns in the data set. Well, the weight vector has that dimensionality as well because you get a part of the weight vector for each essentially feature of the data, right? So the dimensionality is there. So still the same thing, right? Again, go back to lesson 1 if you want to see that, right? And then we have the bias. Which room do I have here? Let's see. Okay. Again, for the layer, right, for this neuron, and that's the bias as it usually is. And I'll explain a little bit more conceptually what that means in deep learning. Like, is it the same thing as a linear system? Basically, you know, kind of like the intercept, right? You're anchoring the data vector, kind of, right? You're like anchoring, let's say, the vector. Now you'd be kind of anchoring the projections, basically, right? Remember we talked about the hyperplane in lesson 1, and we said, what does the bias do? Right? We talked about tilting and rotating hyperplanes. A lot of that, again, still applies. Just mixing and matching a ton of different things here. And then we've got something new. All this is not really that different, right? We set out a weight vector, we set out the data, we're just saying which layer it came from, and we're saying this is happening in one neuron. Other than that, it's still the same as the linear system, right? And the same with the bias, right? All of that. And then we've got this guy here, sigma, I'll just put a dot there, let's say sigma something. Okay, and this is the nonlinearity. Now this is really where you start getting, because you could say, well, why does a deep learning network mush together features? Or not really why, how? We know why, because we want to change the feature space, but how is it actually doing that? This warping of features really comes down to nonlinearity. What do we mean by nonlinearity? I mean, in general, you could say kind of like a disproportionate output given the input. I mean, that's obvious, right? Like if we were to just draw kind of high school level concept, right? Like we think of linearity as input output is very proportional, X, Y, and then obviously nonlinear is not proportional like that at all. We get that. Well, you can mathematically put different versions of nonlinearity into the neuron so that when you apply it to whatever the linear thing is doing, it warps it, it changes it, the output is disproportional to the input, however you want to say that. There's common examples of this, right? There's ReLU, like defining linear units. I mean, you can just kind of just define these. We'll do more of this later on in the lesson, right? Sorry, later on in the course, we'll kind of dig into different activation functions, as they're called, where these nonlinears come from, how they work, yada yada. But don't want to go beyond the scope. I just want to show you that there's math behind it, right? There's kind of like sigmoid or tan H, which is, you could say again, so you're applying the sigma to some sigma here is just kind of the nonlinearity that's being applied, right? Yeah, and it kind of takes on this form with the negative x. And so ReLU, sigmoid tan H, you could say soft max at the output is pretty common. Again, you don't really need to know these right now, but I just want to anchor it in the mathematics. So you see that there's like a mathematical way to define these nonlinearities. So something you might do at the researcher level is, hey, I'm going to come up with different nonlinearities. Of course, people do this kind of thing. Some J, whatever. So you might come up with a different mathematical expression to try to get weird warpings of nonlinearity happening inside your neuron, right? And that's kind of both. I think this is kind of a nice example of how deep learning research can be both an art and a science, right? You can kind of get explicit about how these nonlinearities are supposed to be, but I can guarantee you a lot of these came out from trial and error, actually, right? You could try a bunch of different things. It makes the network go better. You don't know why. You can come up with theories and explanations of why this nonlinearity may have led to improvements. Those are still just explanations, and we're going to cast those into linear sounding narratives, as we always do, but there's a lot of trial and error, what you might call alchemy, mixing and matching. That's the name of the game when it comes to complexity, right? So you can still define things. Here's what I've used. We know it leads to nonlinearity. We know conceptually why that happens. Anyways, I just want to expose you to some of that math. The slides will do a cleaner job of showing you what those equations look like, expressions look like. But, we can mathematically define whatever we want when it comes to this stuff. Okay, so each neuron, again, pause the video, go back, look at that expression, right? Current representation of the data, we got the neuron's weight vector, we got the bias, that's all pretty normal from lesson 1, linear basic simple systems. And then we've got this nonlinearity applied, and that's where a lot of the magic, you could say, comes from in deep learning, as you can imagine, because now you're really mixing and matching. Let's continue on with what each neuron is doing. Now, in this case, the output is not scalar, but actually a vector projection of values. Remember, when you normally just kind of do the weight vector, and you apply it to the data, never had the transpose from the normal linear system, right? You would, by definition, essentially get a scalar out of that. But now we're going to get a vector of projection values, because we're not just applying that kind of linear system once, we're stacking the linear system again and again, not to mention doing all these nonlinear transformations on them. So you actually get a vector of values. So you could say, what the whole layer computes, one way to maybe say that is, here's the data for that whole layer. And, I should be a little less sloppy there. Right? Literally think of it as a vector. and then have the expressions that we want. So we know what we've got, kind of what we expect here, right? And we can index those correctly. Let's say this is L minus 1. Again, the previous layer's representation coming in with its dimensionality. The weight vector for the layer that's coming in, we transpose it like we do. We get the bias for the layer that we're on. And then we're just going to add the sigma for the nonlinear transformation. And then you kind of just stack all those together and you just do it for the next layer, right? So just going to have that again, and this will be the second weight vector. This is still L minus 1. This will be the second bias. So each neuron is doing each thing in here. Here's my circle from the diagram. That neuron is 1. That neuron is 2. You stack it all together, dot, 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 dot. You're going to have the transformation. We're going to have this for the last layer, right? We're going to have this for the last layer, minus 1, and this for the last layer, right? Actually, you know what I should do is, well, same thing, but let me go DL, right, as dimensionality. Yeah, it doesn't really matter. Anyways, we can say like the weight vector has the last layer's dimensionality because of the transformations that we saw last time. Anyways, all I want to say here is that you're collecting all the neurons. Like that's all you're doing here, right? So if you look at the math, right, you can say, well, this is what each layer is doing, which is true, but really what it is just collecting all the neurons into a vector and then getting ready to pass it on to the next layer, right? So this is what defines the new feature space. Okay, ultimately, right? Like everything that we started with here, right? Then we went to a new one, and then we went to a new one. What defines this transformation in the new feature space is essentially this. You have the weight vectors, you got the data, you got the biases, you got nonlinear transformations, you stack them into a vector, and then you pass it on. So a layer in a neural network, deep learning, is essentially producing a vector. And that vector is composed of stacked mathematics that is happening, but we define what each neuron is doing. And each of these goes into the new feature space, which you could think of as new axes in a new feature space, which has a new geometry, which has different coordinates, and the data is now playing in a different playground. Okay. So what is each neuron doing? Well, specifically the weight vector, okay, conceptually again, defines a direction in the previous representation space. The dot product computes how aligned the data point is with that direction, right? Like what's the dot product doing here? Again, lesson 1, we looked at dot products. I don't have to go over that again, right? It's like, give me the data. Now I'm going to like kind of map it along a new direction. It's all about that new directioning. That's what deep learning is all about. Create new projections, point those vectors into new directions. Give me the data, slap it that way. Give me the data, slap it that way. That's what it is. The dot product computes how aligned the data point is with the direction. Remember the weight vector, we'll go back to that kind of learning algorithm at the end of this, which is pretty much the same as what you see in the linear system. Because we've already got all the new stuff, right? We've got the nonlinearity, we got all that. We've got vector representation instead of just scalars. We've got that warping. But when the learning happens, you keep learning new weights, right? For the weight vectors. And so that means what you're learning is different directions for the representation. And then you keep seeing how that original data better aligns, or how well it aligns to those new directions, okay? So it's kind of like saying, yes, I collected a bunch of data from the real world, but I don't know where I'm supposed to put this data to make sense of it, right? I'm going to build facial recognition. I'm going to get billions of photos from people, and I'm going to have thousands or millions of features for each photo, whatever it is. And now I've got all this data, I've got all these attributes, and I've got millions or billions of examples. But what do I do with it? Right? You can't just put it into a linear playground and think things are going to be linearly separable. That's just not reality. That's not complexity. It's not the real world. So you've got to do all these different projections. You've got to come up with different axes. It's, again, conceptually, like you're coming up with new columns for the data. Okay, the neuron's output is the coordinate of the data point along that learned axis passed through a nonlinearity. Okay, say that again. The neuron's output, I know this is really sloppy, I apologize, okay, is the coordinate of the data along the learned axis. That's what any one of these are. Coordinate of the data along the new axis, right, the dot product. Passed through a nonlinearity. Give me the raw data, or from the layer before, whatever representation I'm on, right, L minus 1, give me the data, project it along a new direction, and then warp it. Right? Not to get into charades here. Warp it. and then pass it on. Okay? And that income projection warp is what's happening on every neuron, and that's what's trickling through the network. Okay? A neuron defines a learned direction in representation space. This is not a metaphor. This is literally coordinate extraction. Okay? I'm doing this, but whether you like it or not, that's what deep learning is actually doing. Okay, I want to draw you another diagram because it will, a lot of you have probably seen this one as well, kind of bring a lot of what we said together. Diagrams are good. Don't just do diagrams, do the math. Do diagrams, do math, do movements, right? Understand what you need to get all this to come together. Mix and match it. But let's take a look at kind of a picture of what a neuron does, what neuron is doing. This is super common. You see this everywhere. So I'm going to have a bunch of X's here, and there, this is the incoming data. And then parts of this I don't really like as a diagram, actually, because it's too close to what a neural network looks like, and then it can kind of be confusing. Anyways, this is like a pictorial representation of what the math is doing. Okay, so then we're going to have a bunch of weight vectors here, and we're going to say, we'll subscript it 1, 2, 3, all the way to n, but this is the same J, so this is the same neuron. Because again, we're talking about what one neuron is doing. Oops. Okay, this is one neuron. And we can go 1, 2, 3 to D. Okay. So again, you're basically taking a feature vector, and each of those gets its own weights. Okay, and then you bring those together. Traditionally, they might have called this like a transfer function. I don't think that's super common anymore. But you put a big thing here, and all this is saying is like, this is what we already know. So we've got some output here. The weight vector comes together. It's got the data. It's got the bias, right? And this is belonging to a neuron. And so this is the dot product. I don't know if I even really need to draw. It's the same stuff we basically already. You can think of this as a linear projection right here, okay? But if you're more visual, then maybe that math was throwing you off, and maybe this helps a little bit. And then this continues forward. This is just what the neuron's doing, right? We've already talked about all this, but I just want to put it into pictures. That's that sigma, okay? Now this is sometimes called, or usually called actually, the activation function. Okay, remember we looked at the math, tanh, ReLU, all that kind of stuff, where the activation function is how you do that nonlinearity, right? And so we could say this is, J. We'll say this is just sigma on the ZJ, right? So we got the ZJ here. Everything we know comes into here. So data, weight vectors, linear projection, activation function, and then kind of at the output, you say like, what is the neuron outputting? It's the activation. Okay, and that activation, we're kind of getting used to this, right? Belongs to some real number, right? So this right here is the nonlinear warping of the coordinate value along an axis. Okay? So that's just the picture version. I didn't really introduce anything new there, but maybe that helps you visually see the parts. Again, you have any questions, right? You jump on the chat. What about this? What about that? You said this. Is that really true? Let's talk about it, right? Okay. Now let's just get into some questions you might have, trying to kind of predict what they might be. Why do you have more than one hidden layer? Well, I think that should already be obvious, right? Because we're talking feature learning. Each layer extracts structure at a particular level of abstraction. Now, this is a different way, because you can say, okay, you're learning your feature spaces, right? Blah, blah, yeah, I get it, new coordinates. And I'm not kind of saying things like you want the geometry, you want different projections, or give me the data, project it, warp it with nonlinearity, but why? Like, what does that have to do kind of with the phenomenology of the thing that we're modeling, right? Well, every layer in the network is actually extracting structure at a particular level of abstraction, right? And depth allows simple patterns to compose into increasingly abstract ones. So you see this a lot. It's like, first I'm looking at a picture. Deep learning is looking at a picture, and maybe it gets the edge of something, right? And then it starts to get kind of corners, and then it starts to get the full shape. just like we think of abstraction, defining something higher and higher level, which is what we think the human brain is doing. And we know the human brain uses abstraction all the time, extremely powerfully. I mean, it's really kind of the predominant heuristic that we use to navigate complex possibility spaces and solve categorically hard problems. But formally, if we're thinking about a neural network, right, whatever, all connected, right? It's trickling through, what are these layers doing? Specifically, what are the hidden layers doing? Each layer performs a simple transformation of the representation. The depth allows these transformations to compose into representations that capture higher order structure, right? If you're looking at a chair, you might notice some basic stuff, but I don't know it's a chair. I don't call it a chair yet. Then you notice some other stuff. Okay, and then you categorize this thing at a higher level, right? Or the thing that you call a dog, right? Like, what is a dog? Is it like an animal with a bunch of hair? Well, no, that's got a bunch of stuff. Right? The microscopic details, it's like what is temperature, right? It's a bunch of atoms? Well, not quite. It's a bunch of atoms moving? Yeah, but still not quite. A bunch of atoms colliding, blah, 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 that leads to energy? Okay, we're getting closer, right? We're talking about effective variables. Remember, you got to raise the abstraction to really define a thing, like temperature or a dog. 4 legs, hair, teeth, right? No different than collecting a bunch of attributes, right? That's why you collect a lot of attributes to do things like machine learning, right? But to get the abstraction to know what a thing is, to get the AI to know what a thing is, you got to increase the levels of abstraction as you go, and that's what we do as humans, right? Okay, so I just want to touch on the learning piece because we didn't say anything about how, the weight vectors get better and better and how the learning actually happens. We just kind of said, conceptually we do feature learning, and I talked about what each neuron is doing and what each layer is doing. So there's something I'm going to touch on here. I'm not going to get into a lot of detail because that will come later in the course, but that's backpropagation. A lot of you have probably heard about it. This is really how the representations are discovered. Okay, backpropagate. So let's draw the network again. I'll try to do a little bit cleaner this time. Okay, so we're going to have some network. These are all the artificial neurons. That's our input. These are the hidden layers. That's the output. Okay, we all know that stuff. These are all connected. I won't connect them for the sake of kind of visibly seeing this. Backpropagation, which is the approach, the technique, the algorithm that gets used, propagates an error signal backward through the network, reshaping the learned coordinate axes so that future representations better expose task-relevant structures. So do you remember from lesson 1, we basically had something like this. It's going to look a little bit different, but we said, okay, these parameters, right? We talked about living in the parameter space, right? We had kind of whatever the parameter is now. We had a step size or a learning rate. We have this del or nabla, which is the gradient, and we actually did chain rule calculus. We saw how all this happened, and then we had a loss function. Same learning principle as in linear regression, learning regression. The same thing here. We did this basically, right? We did a gradient on the loss with a step size. We knew that this was basically a vector pointing in the high direction, the up direction, so we minused it off the current parameter to figure out how to get to the low point, right? We said common analogy, someone's looking for where the water goes down to the puddle or the lake or whatever, right? It's the same thing. The exact same expression you could say in deep learning at a high level, okay? What's happening here, though, is backpropagation takes the error that you get right from the loss, again, go look at lesson 1 to see that, and propagates it all the way back through the network, wherever you want to go, and updates essentially the connections, right? So changes the weight vectors. Okay, so gradients indicate which directions matter. That's still true, just like the linear system. Learning rotates, stretches, and folds representation space accordingly. That's what's different with deep learning. So it's the same learning principle as learning in regression, but you're doing it with these nonlinearities, with all the new stuff that the neurons are doing and all the stuff that we talked about, right? Data, projection, warping, right? And backpropagation is just how you get that error. In a simple linear system, you don't have to propagate something through this super deep network. We've got to get that error back to where all the different weights are in here. And think of that as like the synaptic strength, I guess, between neurons, right? That's kind of the analogy way. We think something like that's probably happening in the human brain. I go to learn something, I'm going to learn how to ride a bike. I keep making errors. Okay, so I propagate those errors back throughout my neural net and really kind of distribute which neuron gets how much information, right? How strong the connection strengths are. And so I develop new neural connections. until I eventually have what I need to predict how to move the bike. It's essentially the same idea. So I'm not obviously going into detail about what backpropagation looks like. We will do that. We'll dig into specifically how this happens in a later lesson. But in terms of the governing structure of deep learning and where backprop comes in, I just want to be clear at this point. So the loss depends on parameters indirectly through many layers. Okay? So it's like, you can't just go do the basic, simple, update, right? Because the parameters in the simple systems are directly touching the output. The gradient can just be computed in one step. In deep learning, you've got this buried, nested functions because of the way you're stacking neurons and you're stacking layers together, right? So the loss depends on parameters that are indirectly through many layers. Again, this kind of touches on the black box aspect of deep learning, right? But what about the loss function itself? Like, yes, you still have a loss function. Now, we're not going to pick apart that exactly and analytically, kind of for two reasons, although you still could in some sense. But the loss function in deep learning, first of all, let me just say, it can be identical to the one we already looked at, right? Remember, we basically had, to simplify it, y, pat, and y, right? Like, here's what you're predicting, and here's what the true label is, and you're basically just doing the difference between them. Difference, whatever, some kind of distinction between them. But this guy in deep learning is now a deeply composed function, right? So it's still like, what is this? What is this mapping? What is that function? But you couldn't write it out, right? It's not like you can't explicitly analytically see the math that converts input to output. We don't know what it looks like. We don't even know if it's something you could write out, or it would take too long to write out. Because that's the whole point of deep learning, right? Is it's learning, and this is why you sometimes talk about like universal function approximation, right? Well, the universality comes because this would be like a mile-long function with so many different parameters to it. That's how it flexibly warps in and out of this complex geometry to actually predict what it needs to predict as an output, right? Anyway, so the loss function in deep learning, it can be identical to the loss used in something like linear regression. What changes is the function being optimized, not the loss itself. Okay, so in deep learning, we almost never see the learned function explicitly, whereas in linear regression, we do. That's like a really good way to think about the difference. So again, if someone was just kind of chalking AI up to statistics, that right there shows that there's nothing like that. Very different, even if you kind of start the same way, right? I mean, again, you see like stacked linearities and you think, oh, so it's kind of just statistics. It's really not. Those nonlinearities change everything. So one of the key structural elements that govern the structure of deep learning, right? Nonlinearities, they make geometry malleable. I want that to be something you take home from this lesson. We looked at ReLU, sigmoid, softmax, right? Think of those things as kind of folding space. So things are going to go in different directions, almost like general relativity or something, right? The mass depresses the quote unquote, fabric of space-time, and now things start to move differently, right? Depth of the network allows abstraction to emerge, right? So you might start with basic edges, and then higher levels of abstraction, you might get to actual shapes. You keep going in abstraction, you might get to objects. So it's the chair, it's the dog, whatever it is. You start to kind of get that high level category. Or if this was kind of a natural language processing, trying to understand a document, it might be something like tokens to syntax to meaning. Right? Meaning would be the higher level abstraction, right? Remember, I use that reading example. Letter by letter, word by word. It's not really what meaning is. You got to embed the word in larger sentences. You see higher level structure. Learning happens via abstraction. That's literally what learning is, right? So backpropagation, so nonlinearities, depth, you understand what they do. Backpropagation aligns representation with the task structure. You get error, you get gradients, and you reshape the coordinates. So when the representation aligns with structure, you can say that the decision boundaries start to simplify, because you're still kind of doing the same thing. Like if you got a bunch of data, and some of those are cats and some of those are dogs, and you want to slap something across it so that you know where the cats are, you still have decision boundaries. It's just, this is a ridiculous simplification. I mean, there's no way to visualize some high-dimensional, complex, topological, warped geometry, but it's still a kind of decision boundary, especially for things like classification. I want to know what this is and what this is not, right? So that is going to simplify when the representation aligns with the actual, you might say, problem structure. Learning is going to accelerate. Generalization suddenly improves. That's a common property in complex systems, right? Like precipitation, something precipitates out. Let's use some quick examples. Think renormalization, right? Effective variables, those higher level things, kind of like temperature, replace the microscopic ones. In vision, again, edges, shapes, objects, right? Language, token, syntax, meaning. Okay, these are kind of the structural elements and concepts behind why deep learning is different and really how it works, right? Concepts appear as geometry, not symbols. I want you to think about that. Okay, you're talking to ChatGPT. It seems to have an understanding. This is debatable, but it seems to have an understanding, right, of concepts. What is happening inside the deep learning? They appear as geometry, not symbols. We're trying to find in AI the latent topology of the data manifold. That might not mean anything to you yet. It will if you take the course and you continue on with the lessons, right? Concepts correspond to regions, right? We're talking about geometry, we're talking about spaces, new feature spaces, right? Concepts correspond to regions, relationships correspond to distances, analogies can correspond to directions, similarity can correspond to neighborhood structure, okay? That's what I mean, geometry, topology, the spaces that exist in ways that we can't perceive directly. This geometry is implicit, it's high dimensional, and it's only partially observable. Okay, again, if you want to go tackle explainable AI and ethical AI, absolutely. But don't pretend like it's just statistics, because it's not. Okay? But that structure does exist, and probing works because of everything that we're talking about. The ability to extract structure and get some meaning from it works because of everything we're talking about. In deep learning, it's about finding the right representation. Okay? In linear models, you say, how do I fit the data better? Right? But in deep learning, that's not really what it is. It's what representation makes the structure simple. Because I'm still going to come in and do something like this. I'm just totally operating in the wrong space. The whole point of deep learning is to find what that space is. So that then when you go to slap lines in it, those lines actually make sense now. They're actually discriminating between things that you're trying to discriminate between. Okay, differentiating, right? So, you could say that really, just to kind of give a final little mathematical expression here, so, well, what is learning, right? Learning becomes, we're going to find, let's say, something at some layer, right, such that, kind of mixing words with math here, the function of that at the final layer is simple. Is one way to kind of think of that. Okay? So find, right, that, remember at the beginning I used that phi as just kind of transformation, like find what that is so that the function you're after, which again we can't analytically look at because it's so complex, but that function operates in a way that's actually simple in the sense that we can differentiate between things if it's classification, predict numbers if it's regression, whatever. The function becomes easy in that sense, right, because the space changed. Okay? Because the space changed. So it's still, at the end of the day, this. Okay? Whether you're talking simple linear systems or you're talking deep learning, the difference is deep learning finds the space where this actually becomes far more possible in real world situations and categorically hard problems. Okay? So it's structure, not fitting. Okay? Deep learning works because it learns the coordinates which simplify the parts worth looking at. A simple structure means fewer bends in the decision boundary, fewer exceptions, smoother mappings, right? Lower effective complexity. Not fewer parameters, lower description length, you could say. So deep learning does not simplify reality. You have to deal with reality, right? Linear regression simplifies reality. That's why it doesn't work for most things, quite frankly. Most real world things. Deep learning does not simplify reality. It absorbs complexity into representation, allowing simple operations locally. Okay? That is it for lesson 1B. I hope that all made sense. And again, for those of you who are joining the course, you'll get some nice clean versions of the math and some of the pictures that I draw out on the slide deck. And you'll always have those to look at and to study go ahead and watch parts of the video again, and of course join the chat room on the Scientist AI app to ask any questions you might have. And of course, there's a study space on there to help you learn the concepts, and there's techniques and mindsets that you can practice to keep digging into this stuff. But I hope that gave you an idea of what deep learning actually is, scientifically and mathematically. Okay, until the next lesson. Thanks.